Alright, good afternoon everyone. We start here. So today we'll move on to, actually we'll be able to finish the lesson today and then we'll get some questions done. So last week I'm pretty sure we discussed all the way up to naming compounds. Did we discuss the priority order? We didn't write anything down, right? So we'll start with a question to see whether we remember everything we have done in the past, and after that we will move on to priority order. We'll be finishing that, and from there onwards the last part of the seventh topic is basically about isomers. Isomerism is something very important and very crucial for you to understand clearly. So we'll be moving on to that after the break. Not after the break, as soon as we are done with this part. Okay. So as a small revising of what we have done, we will try to name the compounds. I'll give you just 2 compounds. I think that will be more than enough. We'll see whether you all can name these. Okay. I'll simply name these Are you not very sure about naming aldehydes and ketones? You're not very sure about those, right? Don't know how to do it? Okay. We'll convert these into alcohols. I will quickly do a small, we'll do that also separately. We'll do this, we'll turn this into alcohols. We'll turn this into alcohols, and I'll give you a small briefing on aldehydes and ketones as well. Can you please name these 2? Today is the 16th, right? Right. I think now it's enough time. Shall we discuss the names first? We'll discuss the names first. Okay. So, can someone tell me the name of the very first molecule? We'll take one molecule at a time. Very first molecule, what is the name? 2-methyl? 5-methyl? Okay. Okay, all right. So, fine, that's fine. But for this, you said, now, anyone who has written the name for this one? After the double bond, yes, there should be a hydrogen, sorry. There should be hydrogen here. This one also should be CH3. Right, we'll discuss this now. Now students, the very first question, it's an alcohol with a double bond group here. Alcohol with a double bond group there. So, when you're numbering it, we need to make sure the main functional group in this case, which is the OH, gets the smallest possible number. So, we have 1, 2, 3, 4, 5. Where do I turn from here, students? Where do I turn from here? Do I go to this side, or below? Below, right? So 5, 6, and 7. So this is a heptane, right? Oh, not, I can't say heptane, it's an alcohol with 7 carbon atoms. So when you are starting to name it, you need to first of all identify the substituents. These are substituents, right? These are substituents. Am I correct? Yes? So then, how would you write the name? 2, 3, 5, 5, right? How many substituents are there? Methyl substituents in this particular one that I have drawn. 4 methyl substituents. So then you will write 2, 3, 5, 6 tetramethyl, hept, there are 7 carbons, hept. On the third position we have a double bond, 3 in, and on the first position we have OH group, right? 3 in, 1 all. Did all of you get to that answer? There's this 3 here. What is the issue?
6 does not have it.
Sorry, 5, 5. Sorry, not 5, 6. 5, 5. 5, 5 tetramethyl hept 3 in 1 all would be the answer. Yes. Any other questions from that part? What about this one? If you take this one, which carbon do you get start numbering it from? On the left hand side or from the right hand side? From the left hand side. We will try to give the functional group the smallest number possible. 1, 2, 3, 4, 5, and this would be 6. 1, 2, 3, 4, 5, 6. Even if I went up for 6, still there's going to be only 6 carbon atoms in the main carbon chain, and we only have one substituent here, so there will be 5-methyl. We have hex 2 in, sorry, not hex 2 in, hex 4 in, 4 and 5, here we have a double bond, so hex 4 in, 2 all. So hex-4-ene 2-ol will be the name. 5-methyl hex-4-ene 2-ol will be the name. Okay. So these are just few questions to remind you how naming was done. Let me quickly tell you a few other details as well that are important for us to move forward. Is everyone okay with this part? Bear with me just a second. Okay, so if you can, we will take a small summary of naming of certain things down. For example, we need to know a little bit about aldehydes and ketones and carboxylic acid naming. Now, you will learn about these much in greater detail in the coming lessons, especially topic that discusses oxygen containing compounds. So we have something called carbonyl compound students. Carbonyl compounds. So if you take a carbonyl compound, the characteristic feature is it has a carbon-oxygen double bond. However, it's very important to remember carboxylic acids and their derivatives are not carbonyl compounds. So this is something separate. We are mainly focusing on carbonyl compounds. If you take carbonyl compounds, there are two main carbonyl compounds that we should remember. One is referred to as aldehydes. The other one is ketones. When it comes to aldehyde students, this carbonyl group, on at least from one side, it is connected to hydrogen. Carbonyl compound is consisting of a CO double bond, and on one side it is connected to a hydrogen for sure. So anything that contains this section is a aldehyde. The simplest member of the aldehyde family is this. Simplest member of the aldehyde family is this, because on both sides it is connected to hydrogens. And then the next one is this. Is that clear? When it comes to ketones, ketones basically have this type of connection. Basically, the carbonyl carbon does not have any hydrogens connected to it. It has only other carbon groups connected to it. So it doesn't have to be just a simple CH3 group. It could be anything that connects to carbon. So it could be a CH3 group or CH3CH2 or CH2CH3 group. Anything is possible as long as the carbonyl compound or carbonyl group does not have any hydrogens directly attached to it. It is falling into the category of ketones. The simplest member of the ketone family is this. Then the next one is this. Now naming these compounds are quite simple. Aldehydes have the suffix Al and ketones have the suffix ONE, right? One. So now you are very familiar with naming all the organic compounds, starting from alkanes and alkenes and alkynes, and then we learned about naming alcohols a little bit. So naming of these compounds are no different to that. Basically, only thing that you need to keep in mind is when you're naming these compounds, what do? We what do you call it? Do we mention the position of the carbon when it comes to aldehydes? Why not? They are always in position number 1. So because of that, students, when you are numbering these, when you are naming these, aldehyde always gets position number 1. So then the carbon number 1 carbons are there. Based on the carbon amount, we write ethanol, methanol, so on and so forth, right? So this is methanol, this is ethanol, and then if you have the next member, it will be propanol. Here these ketones, when you are naming ketones, the carbon oxygen double bond, you definitely have to mention the position of the carbon oxygen double bond, or definitely have to mention the CO group's position. Why? Because now in these first two ones you don't have to. First two ones you can just call this propanol, and this is, what is this called? Butanol. Do we have to say butan 2-on? Why not? Because it can only be on the second position, it cannot be in the first position or the fourth position, not possible. If that happens, it will be an aldehyde, right? It can't be on the third position also. If you write third position, then you have numbered it wrong. So these parts, are we okay with these parts, right? So I have broken into categories and given you carboxylic acids as well, right? Last week. Just wanted to make sure that you remember this. So after that, take a new heading. Now these are key parts that you should know about. Last week we did that, right? Aldehydes and ketones. And carboxylic acids also. Yes. So take a new heading. Naming organic compounds. Naming organic compounds. That has more than one functional group in it. Naming organic compounds that has more than one functional group in it. Now students, when it comes to this, again, I have always discussed this a little bit in detail back in the initial parts of the lesson as well. You can have organic compounds, actually not you can, most of the organic compounds you come across, they don't have just one functional group, right? Like for example, amino acids. In your body, do they have just a single type of functional group? No. Even if you take carbohydrates, some of them have both aldehyde groups, or sometimes CO groups along with OH groups as well. So usually most of the complex organic compounds we have in our bodies also never comes with just single functional group. It comes with more than one most of the time. But there are many with just a single carboxylic acid, single functional group as well. So what happens is, when you're talking about these functional groups, when it comes to naming the functional groups, we have to make sure that we use a naming system that is going to only produce one name for one compound. One name for one compound. You need to have one name for one compound. Or if you have a specific compound given, if you are writing the name, no matter where you are in the world, you should get to the same name. If you have written a name, no matter where you are in the world, if you are trying to write the compound formula or structural formula, it should be the same. So when you're trying to do this, we need to make sure that there's some sort of an order when identifying these functional groups. So when naming functional groups, we have introduced a order or a specific hierarchy, I would say, when it comes to naming compounds. So this hierarchy starts from carboxylic acids. So if you take carboxylic acids, they take prominence over any other functional group. Now let's say COOH group along with nitrile group, obviously the prominence is given to this. So therefore when you're naming the molecule, we name the molecule as a carboxylic acid. So the name ends with the suffix that belongs to carboxylic acids. What is the suffix of carboxylic acids? Oic acid. So therefore the name will end with oic acid. And these are referred to as esters. So we'll take this down later. I will give you some time to do that. So this whole bunch, I will erase this part, but I just want to put a small bracket and say that this whole bunch of organic compounds are basically stemming from carboxylic acids. They are all modified versions of carboxylic acids, or we can say derivatives of carboxylic acids, right? So you have to make sure when you are naming these, if these parts are there in a molecule, then usually these will be the priority in the entire molecule. So usually you don't actually have a name for them if they are present as a substituent. Also we don't learn those names. We only learn the names of these guys when they are present as the main functional group of a molecule. Is that clear? Right. So if you take a molecule, I will draw the skeletal structure of a molecule because I just want to be a bit fast about this. So if you take a molecule with more than one functional group, right, more than one functional group, we'll draw something simpler so that you find it easy to understand. So now this is a carboxylic acid with another functional group. So our rules say you have to always give priority to the higher priority functional group, which is this one, and you have to number the carbon chain so that you provide the smallest number to the carbon with the main functional group. So the main functional group is going to be referred to as principal functional group. Principal functional group. The other functional group is no longer considered to be a functional group. We just call it a substituent. Substituent. Is that clear? So it's a substituent. This one is a principal functional group. Other one we see as just a branch or substituent. So alcohols, when you are naming alcohols, usually we use the suffix OL. But when alcohols are present as a substituent, it just becomes what is known as a hydroxy group. So the substituent names are different to their suffixes. Is that clear? As a suffix, this would have been an OL. But as a substituent, its name is hydroxy. Is that clear? Sometimes we may have a carbon oxygen double bond here. What is this section? This is a carbon here. I'm pretty sure you understand the skeletal structures, right? So what is this section? Ketone section. Carbon oxygen double bond. This is a carbonyl group. So out of ketone and carboxylic acid, now ketones are here, carboxylic acids are all the way here. Which one takes priority? Carboxylic acids. So then, can someone tell me how would we name this? This is a substituent then, right? On the third position, we have another substituent. What is the name of the substituent? So we now ketones ends with the suffix ONE. But when it is present as a substituent, we use oxo. Oxo. Is that clear? Oxo would be the name. Is that clear? So these are some common ones. Now I'm just, with this molecule, I'm just trying to show you few common ones that will stay in your mind. I will give you the table and the names. But like, you know, when all the names are there together, some of you, like, you know, don't necessarily give importance to the more common ones. So this is oxo, this is hydroxy. What if you have something like carbon oxygen double bond here on the 6th carbon? What is this one? Aldehyde. Right? There's a hydrogen here. Right? There's a hydrogen here. So this is aldehyde. Aldehyde, we have the suffix Al, but when it is present as a substituent, we call it formyl. Right? So you need to see the entire different names. Right? ON becomes oxo, OL becomes hydroxy, this becomes formyl, right? So different names are like that, students. Okay, so you need to be able to remember all of those names and the rules as well. So we'll start with taking the rules first of all, and then after that we will be moving on to taking this priority order. Actually, there are two other parts, right? We have ammonia, we have halogens, and we have ammonia, halogens, and we have nitro, right? So those three I haven't written down because I didn't have space there. We will write them down on the other side after taking the rules. Okay, so please write a new heading, subheading, guidelines for naming, guidelines for naming organic compounds with multiple functional groups. First rule, identify the longest carbon chain. Identify the longest carbon chain that includes the principal functional group comma other functional groups, principal functional groups, comma other functional groups and all of the multiple bonds, and all of the multiple bonds. And then as a second point, write down, name the or number, sorry, not name, number the hydrocarbon chain. Under that, under number the hydrocarbon chain, point A, right? Point A, please write. Assign the smallest number assign the smallest number. Assign the smallest number to the highest priority functional group. Within brackets, please write principal functional group. Second point, B. When numbering in different directions, if the principal functional group gets the same number, if the principal functional group gets the same number, numbering method that assigns the smallest numbers to the multiple bonds will be chosen. Smallest numbers to the multiple bonds would be chosen. Next one, C1. In the absence of multiple bonds, if the principal functional group obtains the same number, when numbered from different directions, numbering method that assigns the smallest number to the other substituents will be used. After that, please write one final sentence. The rest of the naming rules that were used, in naming other organic compounds can be used from this point onwards. rest of the naming rules that were used when naming other organic compounds can be used from this point onwards. What does that mean, students? What are the rest of the naming rules? After doing this, what are the rest of the naming rules? Can you tell me basically what we do? Now here we have something new happening. What is the only new thing that is happening here? We have substituents as well as a principal functional group. Earlier we had only one functional group, or we looked at slightly more advanced version of that, that is the presence of a double bond or triple bond along with a functional group. But here now we have multiple functional groups. So that is new to us. So what does this say? They say, first of all, identify what is referred to as the principal functional group in the entire molecule. Principal functional group happens to be the functional group with the highest priority. So we identify that. Then we have to start numbering the carbon chain. So you have to number the carbon chain in such a way that the principal functional group gets the smallest number. After the principal functional group gets the smallest number, now imagine you can start numbering the molecule from two different directions. But if you number it from two different directions, the principal functional group gets the same number. Situation like that. At that point they say, prioritize giving a smaller number to multiple bonds. That means the presence of double bonds or triple bonds, we need to prioritize giving a smaller number to double bonds and triple bonds. Is that clear? Other functional groups can be there, but we don't care about them for the time being. We try to prioritize multiple bonds. That's what the ruling system says. If there are no double bonds or triple bonds, then imagine you number it from this corner, this corner. Now we'll do a small example so that you develop a bit of an understanding. So imagine we have a molecule like this, right? Okay, and there's a double bond here. Now if you number it from this corner, so there's another OH group also here, right? There's an OH group also here. So first of all, we identify the main functional group. This is a ketone group, this is a alcohol group. Which one is the main functional group? Ketone. When we are numbering it from both the sides, if I number it from this corner, 1, 2, 3, 4, 5, this gets 3. If I number it from the other corner, 1, 2, 3, 4, 5, still we get 3 here. So now the principal functional group gets 3 either way. Then they say prioritize a name numbering method that gives the multiple bonds the smaller number. So which gives the multiple bonds the smaller number? 1, the very first one, this. Okay, so the one instance, one with red color numbering method, right? So that numbering method is much better for us. Is that clear? So we choose that method over the blue color numbering method, because blue color numbering method gives the multiple bonds larger values like 4, but red color numbering method gives the multiple bonds small numbers like 1. Then if I give you another example here, the same example, but in this case without any other multiple bonds. Now in this case, what do we do? If you number it, it's similar to this. If you number it from this corner or the right hand corner, we are still getting 3 here. Now there are no multiple bonds. Then what do? We prioritize giving the smallest numbers to, apart from this, we look into giving small numbers to substituents. Make sense, no? In any way, students, we like to have smaller numbers in organic chemistry names, organic compound names. But you need to follow the rules. Now you will learn the rules like so, but maybe later down the line when you are writing the names, sometimes you bend them a bit, sometimes you forget. So that's why we do a couple of examples and then learn how to write the names. Is that clear? Right. So are we okay with this part? So here what will be the numbering method, students? You can tell me. Are we using the red color method for the second one, or the blue color method? Which one is better for the molecule that I just drew? Red color method is better. Is that clear? Why? Because when you're numbering it in the red color method from left hand side to the right hand side, the substituent gets a smaller number. Now why didn't I give the substituent a smaller number here earlier? Because there was a multiple bond. The IUPAC naming system clearly states when there are multiple bonds, we have to make sure the multiple bonds gets the smaller numbers apart from the principal functional group. Is that clear? Multiple bonds are prioritized after the principal functional group here. Then only the other substituents are prioritized. Is that clear? Right, so take a small table. Priority order functional groups. Priority order functional groups. So other naming rules you remember, right? Other naming rules what? You write the name of the main carbon chain, the stem name, right? And then followed by AN or EN or sometimes YN based on the situation of the multiple bonds, if it's a triple bond, double bond or whatever, right? And then you have to mention the correct suffix, right? If it's a carboxylic acid, it ends with the oic acid. If it's an aldehyde, it ends with Al. If it's a ketone, it ends with ONE. So those rules are still applicable here, so something to keep in mind. So over here I would like for you to take this table down. I can't write the name in front, no? Right, so please take this down, students. Take this down. I need to extend this table, but once you are done with taking these parts down, I will extend this a bit further. You don't have a problem seeing this part also, right? I told you these guys don't have substituent names. Acid derivatives. Nitrile Once you are done up to this point, there are two more. I will write the other two here. There are only two more after this. So one is one is X. X stands for halogens. The other one is nitro, NO2. So X has the suffix name. It actually doesn't have a suffix name, students. It doesn't have a suffix name because these are normally named as substituents only. So substituent name of this will be halo, and substituent name of this will be nitro. Name those, write those down, please. So extend this to the extend this below. Substituent name. I will draw the line so that you are clear. These are the principal functional group name, or this is suffix, this is sub. Actually, although we write halo, I will explain the halo part, okay? Otherwise you will write halo or halo. It's something I need to explain. Can I erase the first two columns at least? Can I erase the first two columns? First two columns? Fine? I'll erase the first column. Down here also, right? Now, I told you when it comes to halogens, now what is represented there in the functional group section as X basically is a halogen. X is equal to anything like fluorine, chlorine, bromine, iodine. Is that clear? So those are halogens. Now when a hydrocarbon has a halogen connected to it, this will not become an entirely different type of molecule. We consider it to be a alkane or alkyne with a substituent present. Is that clear? So this is just a substituent. We don't consider this to be a principal functional group. So therefore when naming this, we will just mention the position of it, and then this is a halogen. We said the suffix is not suffix, substituent is halo. although we say it's halo, don't write halo. It means the end of the name of the halogen is modified with O. End of the name of the halogen is modified with O. That's why we say halo. Here, so this name would be 1-chloro, 1 2 3 carbons, propane. Is that clear? 1-chloropropane, 2-chloropropane can be there. There can be bromopropanes, whatever the halogen. With an alkane, we will have names like this. Right? For example, another one would be if you take something like this. So now on the second position we have a Br, so it will be 2-bromo, 2-methyl, 1 2 3 4 butane, 2-bromo, 2-methyl butane. Is that clear? So basically it's a butane molecule with a Br substituent. That's it. So the name would be modified with a O. We don't write bromine, we just modify the end of the name with a O. So that's why we say halo. Nitro is also similar. Where instead of writing bromo, if there was a nitro group, there will be 2-nitro. But the LMN, N comes from M, no? So then we'll have to write nitro first. 2-nitro, 2-methyl butane. Is that clear? So that's the situation with these two. They are very low in priority. All the other groups are a bit high in priority. Write a question. Name the following. Name the following organic compounds. Name the following organic compounds. We'll go one by one. Name this, please. We'll go one by one quickly. I'll give you a few examples, but only name this, don't name anything else. Name only the first one. Easy, right? Are we done? First one, no? At least identify the substituents. Done? Don't do the second one. You can copy it. Don't do it too. What is the name of the first compound? 4 starts with 4, is it? 4-hydroxy 4-methyl pentanone. Okay, 4-hydroxy 4-methyl 4-methyl. Okay, so I will explain this part again. Okay, pay close attention. I will come for the second answer. I will double check, guys. Now you all can, I think, come here to the second row if you like, right? So now pay attention. We'll very slowly do this. I don't want to rush it. Just we'll do it slowly. We'll listen to the rules. Okay, very first rule. Rule number 1 when it comes to naming, these kind of compounds. Identify the principal functional group. What is the principal functional group? This. What is this? Ketone. What is this? Alcohol group, OH. Out of ketone and alcohol functional group, ketone is higher. So therefore we go with ketone. Second rule. You need to find the longest carbon chain, including the functional groups. First thing is to find it. Numbering comes later. You find the longest carbon chain including the functional groups. These are the functional groups. So if you go here, the longest carbon chain is simple. You can identify this one. Then number the longest carbon chain, giving the smallest possible number to the principal functional group. So if I number it from this corner, am I going to end up giving the smallest number to the principal functional group? No. So I'm not definitely going to start from here. It's stupid. I can start from here. So then 1, 2, 3, 4 and 5. This is our principal functional group. And then what is this then? A substituent. What is this? A substituent. Is that clear? Now, if you are someone who gets all mixed up with substituents, best to, in a corner of a page or maybe on a piece of paper that you carry around, you can write the names of the substituents. This one is what? 4-methyl. This one is what? 4-hydroxy. This one is 4-methyl 4-hydroxy. Now ask yourself, these are substituents, no? We write the substituents in front always, prefixes. Now when it comes to a name, we have prefix, we have the stem name, we have suffix. Prefix is where you put all the substituent names. All the substituent names along with their positions are written in the prefix. Then comes to the stem name. Stem name is where you write the main carbon chain, right? Like, you know, whether it's having 7 or 8 carbon atoms is indicated in the stem name, like hept, oct or whatever. And then suffix, like, you know, suffixes, parts of suffixes like an, en can be used to indicate the, like, you know, single bond, double bond situation. And finally, you have the suffix. Suffix uses what? Tells us what? The principal functional group. If it's a carboxylic acid, if it's an aldehyde, if it's a ketone, the suffix will tell us that. So over here, these are prefixes. These guys should come front. So which one should be written first? H comes before M, right? So therefore, when you are arranging these, the 4-hydroxy part comes first. 4-hydroxy. Then only the methyl part comes. 4-methyl. So now the substituents are done. Then I turn my attention to the main carbon chain. Main carbon chain has 5 carbon atoms. So then I write the main carbon chain name, pent. Does it have any double bonds between it, like, you know, carbon atoms? No. So it's going to be pentan. If it had a double bond, it will be pent, whatever the position, ene. Right? Position of the double bond, ene. But here we don't have double bond, so we write pentan. AN indicates that this is a saturated hydrocarbon section, right? Or normal carbon-carbon single bonds are present. That's what it mentions. And then after that, we move on to the main functional group. Main functional group is ketone. We have to mention the position of this ketone group. It's on the second place. Pentane 2-on. Is that clear? So this is correct. Or else you can also write 4-hydroxy 4-methyl 2-pentanone. Right? But I prefer that you use only this method. Okay? But know that both are correct. Do the second question, please. I'm sorry students, I asked, although I asked you to do this, I forgot to add the second functional group. I was just writing it here. I forgot to add the second functional group. Can you just give me a second to add the second functional group? Right, you can do it now. Do the second one only. Do the second one only, nothing else. Let me know when you're done. Done with the second one? numbering is correct. Good. 2,4 diet. See, I told you. Yellow part. That's yes, correct. Methyl, 2-methyl. Where's the 2-methyl part? Yeah, 2-methyl. Pent 3-ene. 1. Oh, no need to write 1L. Okay. Pent 3-ene. Otherwise, it's correct. When you're done, tell me. Done with the second one? Now, when the halo part, see whether the order changes because the alphabetical order. Okay. Correct. Don't worry. Correct. Very good. Have you started these parts? That's good. Which one? This one? These are all single ones? Definitely. So I don't want to observe this much. You have this name and this name, right? Definitely the first one. Wait. I can't say definitely this one because it's 2266. Either way you get to 2266. No, the numbers, 4 numbers are 2, 2 and 6s and 6s. Bear with me. You have numbered it wrong, I think. See, there's no ethyl group here at all. Ethyl is here, no? When you number it from here, 1, 2, 3, 4, 5, 6. You say 7, no? 6, 7, 8.
Can we write like that?
Huh?
Can we write like that?
Yeah, we always go bendy, like we keep going down and all that, right? So
We said it is substitute.
why would it be? There are no functional groups here, right? This is pentane molecule. So this looks, we have drawn it looking like a substitute, but we can definitely turn and go. And I'll do like a bit of a bendy twisty one so that you understand. We have to identify the longest carbon chain. Sometimes it's not the straight one. Now here, this one is also somewhat bendy. You have but the thing is, I have given it to you in such a way that you avoid the bends. But we'll do this one. Now students, always keep in mind when a question is given to you, you have to identify the longest carbon chain. It could be bent, right? It's still fine, right? Still, even if it's bent or not, you find the longest carbon chain. Think of it as a snake that is now going all with bends and twists. You don't only look at the section of the snake that is straight and say, this long snake, right? No. But the actual length of the snake is different. So just like that here, also if you take a look at this one, the longest carbon chain would be starting from here, going all the way to this direction. So that carbon chain has 1, 2, 3, 4, 5, 6, 7. 7 carbons. But we don't take it. Why don't we take it in this case? In this scenario, we don't take that to be the longest carbon chain. Because in our rules, we learned first of all to identify the main functional group, principal functional group. Here we have a Cl and an aldehyde. Out of the two, aldehyde takes prominence. This is our principal functional group. Aldehyde is a substituent. So when I'm identifying my main carbon chain, I need to make sure that this is included and so is this. So if I'm trying to identify that carbon chain, it's this carbon chain, right? You go up and then take a bend and go towards this side. So this is the main carbon chain, and then I learn how to number it. So numbering would be starting from aldehyde or the main functional group, which is aldehyde. 1 here, 2 here, 3 here, 4 here, 5. Here, after doing so, you can identify the substituents. We have ethyl substituent at 2. We have methyl, actually students, I have written CH2, I'm sorry, because when I'm writing I usually think of extending that part and I later on forget about that. Every terminal carbon should be a CH3, like end sections should be CH3, okay? So next time if you spot it, let me know. And then here, this one is also a substituent, and this is also a substituent. You have 4 substituents, right? Like no other. That's it. So now when you are naming this, like I told you earlier, write down the substituents. There are 1 methyl substituent, so that is in the second position. So it's a 2-methyl part. This is until you get used to these things. And there are 2 ethyl substituents. So one is connected to the second carbon, the other one is connected to the 4th carbon. So I can say 2,4 diethyl. I have an ethyl substituent section. And another very important one is the chloro one. 5-chloro, not halo, right? Yes, it's a halogen group, and we said substituent name is halo, but I then later elaborated halo stands for bromo, chloro, iodo, stuff like that, like halogen name modified with the O at the end. So now we have these. Now out of these, which one comes alphabetically in the first place, alphabetical order? Chloro, and then ethyl, then methyl. So your name should be 5-chloro, 2,4 diethyl, 2-methyl, and then now the substituents are named, done. Then we move on to the main carbon chain. Main carbon chain has how many carbons? 5. So we write pent. In this particular scenario, the main carbon chain has a double bond. So therefore we have to stop at pent and mention the position of the double bond. 3rd position. Pent 3-en. En is used for the double bond. Pent 3-en or 3-en. Then we have an aldehyde. When it comes to aldehydes, you don't have to write 1L. If you write 1L, you don't get marks because you don't need to write pent 1L. Is that clear? Because we know aldehydes always starts with 1. So we can just write pent 3-en L. Or else what can I do? I can take this 3 in front of pent. Right after naming all the prefixes, the stem name can be written with this number taken to the front. So 5-chloro, 2,4 diethyl, 2-methyl, 3-pent-enal. That is also possible. Is that clear? That is also correct. The reason why I am mentioning that name also is, imagine in an MCQ question, this answer is not there, but the one with the 3 in front of pent is there. You will get confused as to which one is the answer. That's why I mentioned that. Okay? But we usually prefer to write it this way because this is very clear where the double bond is present. Double bond is present on the 3rd carbon onwards. Right? Okay. Copy the name if you have gotten it wrong. Have you attempted this question also? Some of you may have, but please take it down and start attempting this question. Be mindful when attempting this question. I added a few twists there. Can I erase this part? I would like to give you another question with few bends in it, so that you identify. I'll give as many bends as possible. So Prasadi, this one specifically is for you. So let's see whether you get it right. Do the third question for the Ramvik. Right, let's see. Done with the name? This is okay. So the full name, right? Is it nitride or nitrile? Are we done? So let's name this compound. Now, this one has mainly two functional groups. We have the CN group, which is the nitrile group. We have a ketone group, and that's it. So if you take ketones and nitriles, which one takes prominence, students? Nitrile or ketone? Nitrile, right? So right after, amides, before ketones, we have nitriles. So nitriles will take prominence. So it will be given number 1, 2, 3, 4, 5, 6, 7. So here, when it comes to certain cases, if you have written this as a substituent, that is wrong. Is this a substituent? CH3? No, it's in a carbon over here, so this is part of the main carbon chain. So when you're identifying the main carbon chain, don't miss this one out. So on the third position, we have a methyl group, and this is our substituent, now 4. So when you're writing the substituent names, you need to understand there's a 3-methyl part, and apart from that, on the 4th position, we have oxo. We have oxo part. Is that clear? We have oxo part. So now, when you are naming this, it will be LMNO, right? LM, actually M comes first, then N, and then O. So O comes after. So it will be 3-methyl. 4-oxo, 3-methyl 4-oxo, hept 5-ene, 1 nitrile. 5. Actually, students, when it comes to nitriles, it's always 1, just like when it comes to aldehydes and carboxylic acids. Can it be anything other than 1 when it comes to nitrile? Can nitrile be present as, we can have nitrile as a substituent, that's a different story. But if nitrile is the main functional group, if it is the main functional group, it will be 1. Is that clear? Aldehydes also can be substituents, but when aldehydes are the main functional group, it starts with 1. Nitriles also, when it is the main functional group, it will start with 1. So we can just write hept 5-ene. I haven't missed any other substituents, right? So we have 1 here, 2 here. We haven't missed any other substituents. Hept is correct, 5-ene. Nitrile. Usually students, now this is something you don't normally get to name nitriles, but I just wanted to emphasize on this as well. Usually when it comes to writing nitrile names, now when it comes to any other compound, we just write En only, right? We don't write the E part, right? But when it comes to nitriles, we usually do add the E as well, right? For example, if there's a nitrile compound, instead of writing pent 5-ene En nitrile, we just write the E part as well. But in our syllabus, we don't go into that extent and even talk about the naming of nitriles in that detail, because I haven't come across many questions in our syllabus where we have named compounds of nitrile as nitriles without naming it as a substituent. Usually if you see a CN group in most of the questions that we come across, CN is present as a substituent. Is that clear? So we don't usually outline going out of our way that this E part is there. Right, that is special when it comes to nitriles. Some people do write it without the E, but in the international or the books that we usually use, the E is there. Nitriles are named with, like, E here. For example, if you take something like this, CH3, CH2, CH2, CN, right? So this is named 1, 2, 3, 4. 4 carbons are there. We call this butane nitrile. Is that clear? Not butene nitrile. Not butene nitrile. This E is there. Is that clear? So go home and do a little bit of a search on it so that you will come across this detail. Normally we don't usually leave the E out, only when it comes to nitriles. Okay? But maybe because of that particular reason, we don't talk a lot about that in our syllabus. So don't worry, you won't come across it much. Okay, so now if you want, you can take this down, no problem. Last question before I move on to the other parts. Maybe we'll do one more. I didn't do any carboxylic acid parts, so we'll do one more. So now this one, if you take a look at this one, this is again easy one. Can you tell me what is the main functional group here? I actually wanted to do 2 more questions to focus on one. The addition of, now I will do that in a second. So anyway, what is the main functional group here? Ketone or aldehyde? Aldehyde, right? Why is it aldehyde? Because aldehyde is just one above ketones, right? So therefore aldehyde is taking prominence. We will take aldehydes as 1, then 2, 3, 4. Now I have to include this one, so without any hesitation I have to go this direction. 6, 7. Do we go to this side or the right hand side? Right hand side. 8, 9. So I just want to see, we can go like that. Okay. So the substituents here are, this is one substituent, this is another substituent, these 2 are also substituents. Hopefully you won't get something like this at the exam. This is not difficult but just complicated. Not difficult at all, like so many carbons, that's it. So what do? You write the substituent names. There are 1, 2, 3, 4 methyls, my goodness. So we have 3, 4, 7, 7, tetra methyl section, and then after that we have a 2 ethyl substituent, right? And then the last substituent is the oxo one. It is a 6 oxo. So we'll organize them in order. Ethyl, methyl, oxo, right? So we have 3, 4, 7, 7 tetra methyl, ethyl. We start with ethyl, 2 ethyl, 3, 4, 7, 7 tetra methyl, 6 oxo. 6 oxo, we have altogether 9 carbons, so that's non. 6 oxo non, 2 in, 2 in al. It's an aldehyde. 6 oxo 2 enal, right? Is that clear? So that's mainly what I want you to take from this. Now I want you to name another compound that I was planning to give you here. Can you please take this one also down and see whether you can name this compound? See whether you can name this compound. Now that one you have to be careful. I'm pretty sure some of you will get it right. That means some will not. Right, so when you're done, let me know, I will come around. Done? All of your schools are starting, no, you're not. 6th.
January 2nd, I think.
Sorry?
January 2nd.
Second day? Second?
January 2nd.
It's January 2nd? Oh. Not the 6th or anything, 2nd itself. No, but you all had a long holiday, right? Like starting December 1st? How many of you are going to school still? 1, 2, 3, 4. Okay, I want to see whether we can have a paper class, but the thing is, I'm available only in morning hours for a paper class. Anyway, when are your schools done? Like, it has to be finished, I think, in soon, but then it will be, you all go to school, no? We'll see whether we can do something on Saturdays. We'll take a small break after this, and then we'll start the class after a break, okay? Because when I'm starting the next next part, it's going to be about isomers. We'll be able to finish off isomerism today. Hopefully by 7 we'll be done with isomerism. We'll see. Isomerism is not that difficult. Can I name this molecule now? Shall we start? Can someone tell me how many carbons in the longest carbon chain? 5. What is the main functional group? Ketone. Alcohol is there, it's a substituent. So if I number it from this corner, 1, 2, 3, 4, 5. This gets 5. If we number it from this corner, 1, 2, 3, 4, 5, this gets 3 anyway. So what is the rule? If both numbering methods gets the same number over here, then we should be mainly focusing on what? Giving the smallest number to multiple bonds. So we now choose this numbering method. 1, 2, 3, 4, 5. If numbering in both directions give the functional group the same value, we actually prioritize giving the multiple bonds the smallest number. So these are substituents. So when you're numbering it, we have 2 ethyl, 4 methyl, and 5 hydroxy. A, B, C, D, E, F, G, H, I. So H comes after E. So we have 2 ethyl, 5 hydroxy, 5 hydroxy, 4 methyl, 2 ethyl, 5 hydroxy, 4 methyl. I think I'm going to run out of space, students. You should not break the name down into 2 parts, but I might have to. Okay, so shall I write the name here? Write the rest of the name. You shouldn't be breaking down the name though. Bear with me, students. You shouldn't be breaking down the name. I'll start here. 2 ethyl, 5 hydroxy, 4 methyl, and this one has altogether 5 carbons, so therefore we'll say pent. On the first carbon itself we have a double bond, 1 ene, pent 1 ene. On the third carbon we have the carbonyl group 3 on. Now I know Genuinely tell me, is there anyone who numbered it the other way around? Nobody numbered it the other way around? Very good. Right, you are following instruction. I thought some of you will number it the other way around. Good. Right. So is that clear now? I just wanted to double check. Right. So if this double bond was not there, then you would have numbered it from this corner. Is that clear now? Now this is fresh in your mind. Will you forget if I give you a similar question next week? Hopefully not, right? Now this is fresh in your mind. You will remember, but try your best to not let this go from your minds. This is a very crucial, important part. I can give the break at 5 also, then we can take sharp 5 to 5:15 type of break. What do you like? That is fine. Shall we move on to the next part? So the next part is, I think, something that all of you would love. Like, this is something to do with playing around with carbon atoms. So although organic chemistry is challenging, I have seen many students like it. Many students like organic chemistry regardless of the fact that it is. You want the interval now? Okay, alright. I'll take an interval now. We can have a break now. So now it's, I will give you a break now. It's 4:50. Be here by, take a 20-minute break. Be here by 5:10. Be here by 5:10. Take a break. Right. We'll start now. So, the next part is going to focus on isomerism. So, you need to know what an isomer is. So, we'll first discuss what an isomer is. So, isomer is a substance that have the same molecular formula for the organic compound we are referring to. So, organic compounds can have the same molecular formula but different arrangement of atoms. Okay? We can talk about, when we say different arrangement of atoms, we are referring to the connectivity of atoms, how they are like, connected to one another, as well as different spatial arrangement. We'll explain that a bit later, right? So basically, they have the same molecular formula but different arrangement of atoms, both connectivity wise and spatial arrangement wise. This produces few different types of isomerisms. So if you take, now in our syllabus we use this very strong words like constitutional isomerism, diastereoisomerism, all that. We start with the simple normal words that we usually commonly use. So if you take isomerism, it is broken into mainly two parts. One is what our syllabus refers to as constitutional isomerism. Simple terms, structural isomerism. So the structural isomerism is the simplest one, and the next one is stereoisomerism. Stereoisomerism. So stereoisomerism and structural isomerism are the basic ones that we have. So structural isomers are then later divided into three main types. Our first one is referred to as chain isomers. Students, since I want to save a bit of space, because I'm going to give you some examples here, I don't want to keep writing chain isomers. The isomer word I will not write. Okay, so chain isomers, and then we have position isomers, and we have functional group. Chain, position and functional group. I will briefly explain each of these when I am giving you this flow chart, and afterwards, students, I will give you a subheading chain isomerism, and I'll give you small definition, and we'll do a question, right? That's how we progress from here onwards. We don't have to copy down all the theory parts that are in the textbooks or anything. We understand what chain isomerism is, and we'll be doing some questions to see whether you understand that. Is that clear? And then we do the same for all the other isomers as well. So we'll first understand what chain isomerism means. Now if you take a molecule, example, the molecule that has this formula, let's say C5H12, this is an alkane. We can write the structure of the alkane like so: CH3, CH2, 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 CH2. Bear with me, I don't want it to go to that side. Okay. Now, this can also be, this particular same molecular formula can be also observed in a few other molecules, such as these ones: CH3, CH, CH3, CH2, CH3, and also this CH3, Now in each of these cases, if you observe, the main carbon chain's length has changed. Here the main carbon chain has 5 carbon atoms. Here the main carbon chain has only 4 carbon atoms. Here this one has 3. Is that clear? But the molecular formula is the same, C5H12. But the length of the main carbon chain has changed each time we played around with the connectivity of atoms. The connectivity, the way in which the atoms are connected to one another, has changed here. Earlier we didn't have each carbon connected to more than 2 carbon atoms, like in the middle. But here we have one with 3 carbon atoms connected to it. Here we have one with 4 carbon atoms connected to it. So connectivity has changed. So usually in the structural isomerism, what we see is a change in connectivity. How the atoms are bonded together. Atoms are rearranged. We have some atoms here, we bring it somewhere else. We rearrange the atoms. So that is chain isomerism. Did you understand the example? Right? So the chain, longest carbon chain's length has changed. Then we move on to position isomerism. Position isomerism. Position isomerism mainly refers to a substituent changing its position in the carbon chain. Sometimes it can be the first position, it can be the second position, it can keep changing its position. Right? So then you get to different molecules. When you are naming, you would know the names of the molecules will be different based on the position of the substituent. So for example, now if you take something like, we'll take an example, you don't have to draw a line like this when you're copying it down. I just want to separate the two. So if you take something like C4H9Br, C4H9Br. So then we can have this situation. The bromine group is in the first carbon. Bromine group is in the first carbon. Or we can also have another one where the bromine group is in the second carbon. Now I can't draw another one by shifting it to the third carbon, because if I shift it to the third carbon, the name of the molecule is still the same. 2-bromo-butane, right? This is 1-bromo-butane, this is 2-bromo-butane. What was the only difference between the two? This one is connected to the first carbon atom here, and the position of this functional group has now changed to the second carbon. Is that clear? Simple. Position isomerism. You simply change the position, but when it comes to position isomerism, we are not bothered to change the carbon chain's length. Okay? Is that clear? We can combine the two types of isomerism and draw something like that. That's a different story. What I'm saying is, if I'm just talking about only position isomerism, we don't bother to change the carbon chain's length. We keep the same carbon chain, we keep changing the position of the functional group or whatever the substituent we are referring to. Is that clear? Right. And then finally we want to talk about functional group isomerism. Functional group isomerism. So functional group isomerism is a nice one, students. Now that one requires a bit of understanding. So for example, if you take an alcohol like ethanol, its molecular formula is C2H6O. Ethanol's molecular formula is C2H6O. So one formula that it has, so ethanol can be written like this: CH3, CH2, OH. This is ethanol. This is ethanol. Now, what makes ethanol an alcohol? The OH group. Anything that has only the OH functional group will be referred to as an alcohol. If there are other functional groups, then it will be named accordingly. This one has only this functional group. This is an alcohol. Now, if you change the connectivity a little bit, you can get to something like this. Now this is not an alcohol. This is referred to as an ether. Now naming ethers are easy. you see what are the R groups that are connected here. You don't have to naming all the ethers, but what is the R group that is connected here? Methyl. How many? 2. So we call this dimethyl ether. Is that clear? Dimethyl ether. Imagine this one is a ethyl, this one is a methyl group. This one is ethyl, this one is methyl. Alphabetically, which one comes first? E. So we call it ethyl methyl ether. Is that clear? Simple. So anyway, this is dimethyl ether. We don't learn ethyl ethers like the way we name, like, aldehydes, ketones and stuff like that. We rarely look into ethers, but we use ethers in organic chemistry a lot. But we'll come to that later. So do you understand that these two are functional group wise different, molecular formula wise same? Is that understood? So these are called functional group isomers. Isomers are basically having the same molecular formula, different connectivity or different spatial arrangement. Is that clear? Do you understand? Right. So then when it comes to stereoisomerism, because now I have utilized most of the space. Shall we copy this part down? Right, so we'll take a new heading. Isomerism. We'll take a new heading, isomerism. Under isomerism, please write isomerism arise due to molecules with the same molecular formula. Isomerism arise due to molecules with the same molecular formula having different connectivity between the atoms or having different spatial arrangement between different molecules with the same molecular formula. Having different spatial arrangement, students please include arrangement of atoms between, having different spatial arrangements of atoms. Of atoms part is important. So it's either connectivity that gives rise to isomerism or the spatial arrangement differences. Connectivity or spatial arrangement differences. So these are connectivity, right? The structural isomerism is usually arise due to connectivity differences. Here we can see like they are connected in a specific manner. Then now when it comes to second isomer, the connectivity is different. Here also the same. Connectivity is different. The whole spatial arrangement part. Spatial means how atoms are arranged in the three-dimensional space. The spatial arrangement part comes under stereoisomerism. How, like, there's one atom here, another atom here, another atom here, another one here, right? Sometimes these things can get slightly changed. In 3D space, arrangement can change. This could cause the molecules with the same molecular formula to be distinctly different from one another. They have the same molecular formula, but they're different to one another, right? They sometimes might have the same connectivity. That's a surprising part. They have the same connectivity also sometimes. I'll show you. They have the same connectivity sometimes. Connectivity wise, they are absolutely the same. But spatial arrangement wise, they are different. Right? You will understand it when I'm talking about stereo. So did you take this? Can you please, when you're, okay, bear with me a second, students. So when I'm talking about stereo, let's see whether I can actually climb. There's something called geometrical isomerism. Right? The other one is called optical isomerism. Geometrical and optical. Geometrical and optical isomerism. Geometrical isomerism is commonly referred to as cis-trans isomerism as well. Arise due to carbon-carbon double bond. Arise due to carbon-carbon double bond. And here, this is optical isomerism. Usually arise means is they are due to chiral carbon, or in other words, carbon with 4 different groups. Right, so for the time being, take those down. I will anyway elaborate every single isomerism separately. So for the time being, please take these down. Structural isomerism, stereo isomerism. I know this flowchart looks a bit different to what is in the textbook, but these are the most commonly used terminology instead of diastereo and stereo and constitutional isomerism. So you need to know. So basically take this same graph, superimpose it on the graph, same flowchart, superimpose it onto your textbook flowchart. It's the same thing. Okay? Constitutional means structural, diastereo is geometric, optical is basically mainly the stereo isomerism we are referring to. Now I will give you that part separately. Cis trans and optical isomerism part, I will give you the note separately. It's something for us, it's difficult, no? Right. Are we all done taking it down? Only some. I'm going to erase this section. I'm assuming you all are done with that section. Okay, so write down a new subheading, chain isomerism. Chain isomerism. Chain isomerism is a type of structural isomerism, but I want you to take a small note and a question after that. Okay, right? In chain isomerism, we can observe that the molecules have the same molecular formula, but the length of the main carbon chain is different in different molecules. So as an example, we are doing a question. So when I say example, you write example and then write the question. So you will answer the question. When you're studying, you will see you have example done, right? So as an example, let's write a small question. Write EX and then write the question. Write all the chain isomers. Write all the chain isomers that can be drawn for C7H16 formula. C7H16. Please do that. Do it fast. You need to improve on your speed a little bit. This is the first one. I have drawn the first one. Don't look up. How many did you draw? Altogether 4. Good. Correct. Now students, this is a part where you have to think a little bit, like organic chemistry, isomerism parts actually utilizes your ability to think and critically analyze certain situations. So if you can, if you are anyway good at analyzing things and getting to answers, you will be finding this easy. Did you get to these 4? It doesn't have to be these exact 4. What I'm trying to say here is, you have to draw one molecule with 7 carbon atoms in the main carbon chain. You have to draw another molecule with 6 carbon atoms in the main carbon chain. Another one with 5. Another one with 4. Okay, drawing one with only 3 would be difficult. For example, if I take this off and put it here, then the longest carbon chain will be 4 carbon atoms long. Do you understand? So, you can't just shift it however you like and expect it to be the longest carbon chain, right? So it doesn't have to be this substituent CH3. It doesn't have to be here. It could be here. It could be here. It could be here. Anyways, okay, as long as the main carbon chain's length is 6. Here, this one I have put both the substituents in the second carbon, but it doesn't have to be there. It could one could be here, another could be here. Or one could be here, another could be here. Doesn't matter as long as the main carbon chain's length is 5. Is that clear? So we are changing the length of the main carbon chain. We are changing the length of the main carbon chain. Do you understand? Did you all write one molecule with 7 carbon atoms long carbon chain, then 6, then 5, then 4? Right? Did you get to the 4th one? How many of you got to the 4th one? Right, only 1, 2, 3. Others, what happened? Where did you get confused? I think, wait. This is okay. This is also okay. This is correct. This is correct. 1, 2, 3, 4, 5. Right? 6, 7. So this is 5 carbon atoms long. This is correct. 1, 2, 3, 4, 5. This is wrong. This one you have to erase the last one. Right? You didn't write the other 2. Did you understand this though? What about you, Pasni? Got it? Got it now? That's all? Understood it or?
I overthink.
You know, you did a little bit of overthinking, right? Is that clear now? Yeah?
So here can we like attach the EN to him?
Attach the,
EN here, painting.
you want to write, you want to see whether pent and en can be written together.
Yes.
So you can do that by bringing one in front. So then it will be, this whole section is there, and then 1 dash pent en 3 on. Is that clear? Whenever, now we stop the prefixes here, no? Right? And then we start the name of the main carbon chain. Then we have these numbers right after the main carbon chain stem name, we have a number, right? Whatever the number it might be. It usually can be brought forward. Okay? But you can't completely erase it. You have to bring it forward and write it. Then it will be 1 pentene 3 on. If you have questions like that, please ask. Right. Is that clear now? Yes? You got it, right? Anyway. Right, so we need to be very careful moving forward. If you, now is that clear? Yes? So isomerism is a, like I told you, like before I gave you the break, students like this one because it's challenging and at the same time, like, you know, it uses, like, you know, it's like, don't you find this a bit more interesting than other parts of chemistry, like arranging atoms here and there and all that? Do you find it interesting? Some of you do, I think. So anyway, we'll move on to the next one. Next topic. So this is the example. We'll be doing multiple examples that take all of this into account, right? Structural isomerism is one category. Under that, there are 3 types. So when I'm giving you a final question, you will see, like, you know, we take into account all 3 types of isomerism when we are just talking about structural isomers. So the next one, write down next subheading, number 2, position isomerism. Position isomerism. Position isomerism. Write down. In position isomerism, positions of the substituents are changed to obtain different molecules. Positions of the substituents are changed to obtain different molecules with the same molecular formula. Position of the substituents are changed to obtain different molecules with the same molecular formula. Within brackets, please write. Within brackets, please write. The length of the carbon chain remains the same. The length of the carbon chain remains the same. That's something we usually do when we are only focusing on the position isomerism. Let's write a question. Write a question. Write down. Now I'm seeing whether you can think. Okay, so this is thinking. So then write down a question. Draw all the position isomers for the molecular formula C4H8Br2. C4H8 Br2. You may have more than 2, okay? So, like, try to write every single one. I said all. I believe students that's enough time. Okay, how many did you manage to draw altogether? 4. We have 5 here. How many did you draw? 5, right? How many did you all draw? 5. 8? Right. Let's see. What about Praveen, Kavin, Tisa? 7, right? Let's see. So now, students, I'm going to teach you how to draw structural isomers, especially position isomers, safely. First thing to do is, if there are 2 of the same kind or 2 of functional groups, the easiest thing to do is draw the skeleton like so. You can fill in the hydrogens later. Put both of them in the same carbon first. Easy enough, no? Can do. And then shift it. shift both of them to the next position. So this is one isomer, this is another one. Now can you tell me, if I shift it again to the right hand side, can I get a different one or the same one? It's the same as this. So therefore I can't do that. I will stop here. And then the next one is I start with bromine with adjacent carbons like so. And then I separate them little by little. So I started here and then I put it here. And then again, same story. I keep separating them. Okay? Now, after doing so, we have drawn all the ones that we can do by keeping bromine in the first carbon and keeping these separate little by little. So the next one is you bring them together to the middle. So we can bring bromine, this one to the middle, this one also to the middle. Now in this case we only have 4 carbons, but otherwise you can keep bringing them to the middle little by little. Is that clear? So now that's one way to do it, like a specific method that can be used to get to the isomers. Is there anyone who has drawn anything other than these 6 that can be considered an isomer of this particular same formula? I haven't filled in the hydrogens, I'll fill in the hydrogens, don't worry. Is there anything else that can be drawn? You can analyze and see. Can it be anything else? Can it be anything else other than the ones that I have drawn? No, I can't think of any. Is that clear? So this is going to be CH, this is going to be CH2, CH2, CH3. This is going to be CH3, CH2, CH3, CH2, CH, CH2, CH3, CH2, CH2, CH. You need to know how many hydrogens to add here. Why? You can count the number of bonds on each carbon, so the rest you will add. The rest you will add as hydrogens. Here there are 3 bonds, so then the other bond is hydrogen. Here there are 1, 2, 3 bonds, the other bond is hydrogen. Here there is only 1 bond, the other bonds are hydrogens. Is that clear? So these are just the position isomers, okay? For this same formula, I will do another question later on. You can draw many other isomers, but these are just the position isomers. Okay? You will see in a second. Right, anyway, is that clear? These are just the position isomers. I keep repeating it because it's important. For the same molecular formula, I can draw structural isomers. Structural isomers, number will be greater than this, slightly greater than this. Okay? So is that clear? Did you get to 6? Right. So copy them down. Can I move on? Because I need to do geometric as well as optical. So important parts, optical especially. Quickly. Shall I move on to the next one? Right. So take down the last one, functional group isomerism. Third one, functional group isomerism. Okay, under that please write in functional group isomerism, molecules with the same molecular formula can have different functional groups due to differences in connectivity between atoms. Write example. Okay, write the functional group isomers you can write, or draw the functional group isomers that you can draw for the following molecular formula. First one, there's two questions. There's two molecular formula given. Do it. You have to look at the formulas, like just start sketching and see what kind of a compound it is, whether it's a alcohol, carboxylic acid, ester, aldehyde, ketone, I don't know, whatever it is, you can find out. We'll start here. First one is done. Oh, okay, very good. Yeah, that is correct. That's the second one, no? Now the first one. Now when you're writing OH, always put the O towards the carbon side because H can't form 2 bonds, no? Okay, so you're right. This is correct. But what about the like?
Yes, I'm trying to run.
Right. So this is for the same formula, right?
Yes, sir.
These two. Only 2 are there, but the second one, do you see? 1, 2, 3, 4 carbons are here. And double check that answer. Otherwise, the functional group is correct. First one, are you done? Yeah, correct. That is correct. Wait. This is the first one.
I didn't say.
All right, very good, correct. What about the first one? Yeah, first one is correct, but not completed yet, right? Now you are also doing something that I saw in the. Can I have the pencil? So now, when you're writing these kind of formulas, try to show the connectivity a bit. Okay, OH. Now we do write it like this. It's okay, but try to put the O towards the side where the carbon is. Right? So then you know the connectivity is through oxygen. Now here this looks like oxygen is connected to hydrogen. Hydrogen is connected to carbon, but it can't be. Hydrogen can't form 2 bonds. No? We're trying to complete the formula. This one. We learned about. This one is correct. Good. This one is done. These 2 are correct. You don't need this one actually. This is correct. This is correct. These 2 are correct. And this one is not needed. Okay. Yes, it's also correct. You can draw another one though. You can draw another one. If you are quite interested in drawing another one as an alcohol, you can. But you have to think. Now students, I think all of you have gotten to your answers, but some have gotten more answers than others, which is good. So this one, of course, you can see the number of carbons and hydrogens and oxygens says that this is mainly saturated, or each carbon is holding the maximum number of hydrogen possible, because 3 to 8 hydrogens. So therefore this could be something like CH3, CH2, CH2, OH. Right? Show the connectivity of O to the carbon if possible. So this is an alcohol. The other one could be CH3, CH2, CH3. This is an ether. Specifically ethyl methyl ether. This one is propanol, propan 1-ol. Right? So this could have been a propan 2-ol as well, but we don't care now because we are mainly looking into functional group isomerism. Is that clear? So this is one functional group, alcohol. That is another functional group, ether. Now this one doesn't have the right amount of hydrogen to go with all the carbons to form a saturated situation. Right? So that means hydrogen number is slightly less than what it should be, meaning this could be having a double bond somewhere. So this could be either aldehyde or a ketone. See, carbon oxygen double bonds are there. Now I saw some of you didn't stop there. You wanted to look for another one, which is good. Right? Some of you didn't stop here. You wanted to find another one. Yeah, there can be another one. Right? This one has how many hydrogens? 3 here, 3 here. Carbon-carbon double bond is present and a OH group is present. This is a aldehyde, this is a ketone, this is the enol, right? Double bond and OH group. Usually if the double bond is directly connected to the carbon with the OH, it's not very stable. Those kind of enols are not very stable. So anyway, in this question we didn't ask about the stabilities of compounds, so we asked you to write as many different functional groups that can be formed with the same formula as possible. So this is another possible one, right? So this is correct if you are looking for another one. So yeah, so these are the answers you get. So functional group isomerism, done. Write down one final question. Before you do, please take a small sentence. Please take a sentence. When considering structural isomers, the 3 types of structural isomerism can overlap to produce many isomers for the same molecular formula. Many isomers for the same molecular formula. Okay, so after that, please write a question. Write all the structural isomers. Write all the structural isomers for this molecule. So for this molecular formula. All the structural isomers for this molecular formula. Keep in mind, students, just to let you know, here we can't get a different functional group here. Bromine is just bromine, so we don't have functional group isomerism overlapping here, but you will see the overlap of chain and position isomerism. You will see when you keep drawing. Okay, do that please. I have drawn the ones that we drew earlier. I didn't do anything else. But we drew these earlier. Can I see? These are the first 6, no? And this one only, after that. Only one additional one. 1, 2, 3, 4, 5, 6, 7. Okay, okay. You can draw 3 additional ones. Shouldn't have said it though. These two are the same. These two are also, oh no, those two are different. Actually more than 3 you can draw, I think. But I assume it's at least 3. So now we have already drawn 6 now. Minimum 9 should be drawn. Anyone has gotten to 9? 8. Right? Shall we do it now? Anyone who has gotten to 8 at least? 8 different ones. How many? Chandni? How many did you get to? All together? No double bond. Now how do you know there's no double bond? Because all the number of atoms, if you add them together, it comes to 10. Right? C4, 10 different atoms. Let's see, that's enough. Otherwise it will take a long time. I want to do geometrical isomerism as well, but still I think I have been, these are things that we have already drawn. So for just to draw another 3 different isomers, I have given you enough time. So let's see. If you take the next thing is to put or add a branch, right? Next thing would be to add a branch. No? Now we have 4-membered carbon ring. I said there's an overlap of when it comes to structural isomerism. It's not just position, it's not just chain, it's not just functional. All three together is structural isomerism, right? So we can have a branch here. So when you have a branch here, we can have both the bromines on one carbon. That's one type of isomerism. One type of molecule, right? So now this is a different one. Now just because I keep taking these into this other carbons, does it mean they are different isomers? Now imagine I take these two and connect it to this carbon. Now is there a different isomer? No. If you're numbering and naming it, you start with this as 1, 2, 3. When you're numbering it, will be 1, 1 dibromo propane. Dibromo 2-methylpropane. 1, 1 dibromo 2-methylpropane. No matter where you put these bromine double bonds, when you're numbering it, you have to find the main carbon chain. Main carbon chain will start from here, right? Here also the main carbon chain is this with a 3-membered carbon. If you put the bromines here, the main carbon chain will be this section, right? So then there will be a methyl group as well as 2, 2 dibromo group. So 1, 1 dibromo group, not 2, 2. So do you understand? So writing 2 bromines here is not needed. It's the same as writing the 2 bromines here. Or if you bring this all the way to this corner, it's the same as keeping it here, right? So this is one isomer. I have seen that some of you have done this also. That is also correct. Now imagine you put a bromine here and a bromine here. Very good, correct, right? Not bad. What is wrong is you have done this. What is wrong is you have done this. You put a bromine here and another bromine here. Isn't this the same as this? What is the main carbon chain here? 1, 2, 3. On the second position you have methyl group. What is the main carbon here? 1, 2, 3. In the second carbon, methyl group. Isn't it the same thing? Right? Okay, and please keep in mind, students, in organic chemistry, moving forward, you need to have this understanding. This carbon is connected to other carbons, the middle carbon here. So these 3 carbons that are connected to this central carbon atom is basically similar to one another. Having both the bromines on this carbon is equivalent to having both the bromines on this carbon, because these carbons are similar. Clear? So because of that, when you are adding bromines, be careful. But keep in mind, now we have added 2 bromines to similar carbon atoms, so that's fine. The next possibility is to add 1 bromine here, another one to a bit of a unique carbon, which is this one. That's different. You don't have anything else like this here. So therefore, this is a different isomer. Is that clear now? So these are the 3 that you could form. These are the 3 you could form. Is there anything else that you can form? No, that's it. That is it. So we'll add the hydrogens here and complete this. Hydrogen, hydrogen, CH3, CH3, CH2, hydrogen, CH2, CH3, CH2, CH3, CH3. Okay, so this is how you would draw it, students. Double check whether the hydrogen number is correct. Hydrogen number is correct. So altogether 7 are there. Write down a question, go home and do it. This one you can draw actually, when I drew it, close to 10 or more than 10. Write down another question. Right? Any question? You have a doubt? Tell me, it's okay. What is it? Tell me, what is it? What is the issue? Huh?
Can we draw it like this?
Can't we draw it like this? We have 1, 2, 3, 4. Now that's a good question. Bear with me, students. Now I will explain that because many students have this issue. Okay. So tell me if I'm drawing it correctly. Tell me if I'm drawing it correctly. CH3, CH2, CH, bromine, CH2 bromine. Am I correct? Now if you are getting like, if you feel like can't we draw it like this, first thing to do is see if this is a branch or part of the main carbon chain. Is this a branch? Just because you have drawn it down, pointing down, does it become a branch? Actually no. Whenever you have a carbon chain like this, now you think this is the main carbon chain, no? But this is the corner carbon at that point, right? Whenever corner carbon is connected to another carbon, it is not a branch. It's a part of the main carbon chain. So this is a main carbon chain. This entire thing. Yes. So this is having 4 carbons here. So here in the first and the second position, we are having bromines. Right? 1, 2, 3, 4. We have that. Do you understand? So keep in mind, students, it's a common mistake many students make, right? Like when you're drawing isomers, like when you're in the rush heat of the exam also, sometimes you draw a branch like this thinking, this is a branch. This is not a branch. This entire section is the main carbon chain. Is it understood? Clear? So you have to follow the longest carbon chain. Okay? I gave you a question like this, I remember in the beginning, right? Like when we were talking about naming molecules, I did trick you with a question like this, remember? So anyway, we'll move on. Are we okay with this part? Can you take down a small question? Take a small question down. Write all the draw all the structural isomers for C4, H8O, C4, H8O. Okay, so at home please try your best to draw all the structures for this, not here. C4H8O. It will have about if I'm not mistaken, I saw 11 last time, 11 or 12 when we did it last time. I can't remember, it's been a year now. So that's the question. Okay, so go home and give it a try. Okay. Now we move on to geometrical isomerism. We'll finish optical isomerism and geometrical isomerism here. These are simple parts, but I want you to have a good enough understanding of this. So, geometrical isomerism. Now students, geometrical isomerism arise or is there due to carbon-carbon double bond. Now let me explain that to you. You are going to take the same diagram as well. If you take a carbon containing compound, let's say something like this, CH, and then we have a bond coming towards you. We'll take that to be Cl, right, and another bond that is going behind you, that is, let's say again a hydrogen, right? So now if I take this conformation of the molecule and ask you, now this is the actual 3D diagram, no, this is how, now you draw molecules like this, C, H, Cl, H, this is how we draw it. But in reality, this is how it is, no, tetrahedral arrangement around each carbon. Each carbon is sp3 hybridized. So therefore, it's tetrahedral around each carbon. That is clear, no? So because of that, students, this is the actual scenario for each carbon atom. Now if I ask you whether this arrangement of atoms, so this particular molecule, and if you are asked to compare another molecule that looks like this, if I ask you if these two molecules are the same, are they the same or are they different? Are these two molecules, they have the same molecular formula of course, I'm asking, are these two absolutely the same or are they two different isomers? Different isomers, please raise your hands. Right, different isomers. Who says absolutely the same? Absolutely the same. Right, so I have two students saying absolutely the same. Answer is they are absolutely the same. They are not two different isomers. Why do I say this? Because if you take this bond, the single bond over here. Now, for example, the connectivity here is the same, right? So connectivity, carbons and hydrogens are bonded together, and chlorines and carbons are both. See, same connectivity here. So that is something we can agree on. Now because of the fact that chlorine is up, many of you said this one is different to that one because chlorine is up here. Earlier chlorine was in the same level. Now you are saying this is pointing up, so therefore this is a different one. The reason why I say no, they are actually the same is because this is a single bond. Carbon atoms connected to the single bond can rotate. There's rotation. Imagine you have a pencil, you have like two oranges stuck to a pencil. You can hold one orange and can't you spin the other one? Don't waste oranges, you can take cruciform balls and do this also. So what happens? If you connect, what happens? You can spin, like you can keep one stationary and you can take the other ball and you can spin it through this axis. Possible, no? So when it comes to these carbons also, these carbons, every single bond actually has this rotation. They can have it. Now when you want to picture it, picture a spaceship like in these movies. They show like in the initial parts, the spaceship is moving like this, like that. These bonds can move, not bonds, like groups can rotate across a single bond, across this single bond, it can rotate. So therefore students, this can rotate. Imagine this rotated this way. What happens? Chlorine goes here. This hydrogen, I will call it hydrogen dash, just so that I can label it properly. This hydrogen, it comes here, right? And this hydrogen over here comes all the way down here. Keep in mind, when I'm drawing the 3D diagram, I draw hydrogen like with a massive separation. But in reality, they are separated by the same angle, 109.5, right? So this one only doesn't like travel a lot. It travels the same amount as the others, right? But when you are drawing it as a diagram, that is how it looks. So what happens? That chlorine has gone here. That hydrogen with the dash has come here. Hydrogen that was here is now here. This can keep rotating. It can keep changing. Just because we draw it differently doesn't mean those two are different. Is that clear? These two are the same. So you can say conformation is not fixed due to rotation across carbon-carbon single bond. Okay? But that story cannot be applied to carbon-carbon double bonds, unfortunately. Carbon-carbon double bonds are like the strict parent. They don't allow rotation, no going out. Stay here, study. Right? So, if you are basically, imagine when the molecule is getting formed, when you, like, certain chemical reactions happen, and when the molecule gets formed, if the double bond gets formed like so, keeping the chlorine groups here and the other chlorine groups here, and in this molecule chlorine groups both facing down, then that conformation is fixed. Conformation means atoms are fixed in that arrangement. Why? A double bond will not allow rotation. Right? Imagine now, earlier through a single bond there was rotation. Now picture you take an apple and then you put two straws or two pencils through it. Can you rotate that apple then after that? Single pencil, yes, but two you can't. Why? The two axes will not allow the rotation. It will restrict it. Now even here when I'm trying to rotate this, it stops me at one point. When it comes to double bonds, it's even like, although we say this analogy, in reality a double bond looks like what? So we have this type of situation going on, right? Right? Double bonds are even worse than just having two axes. No rotation possible because these two are holding the molecule in this particular conformation, period. That's it, right? It will not allow rotation. So double bonds will not allow rotation. They restrict rotation across the double bond. So therefore, students, if chlorine groups are over here, they can't nicely rotate and come to that arrangement. Okay? These guys can't rotate and nicely come to this arrangement because the double bond won't allow it. Is that clear? So these two are isomers. These two are isomers. Clear? And if you take, now you need to know this as well. If you take a look at the similar groups of this kind of molecule, if the similar groups are on opposite sides across the double bond, keep in mind across the double bond. Across the double bond, if similar groups are on opposite sides, we call it the trans isomer. Trans, opposite. If similar groups are on the same side across the double bond, we are starting here, we go across the double bond, come to the same side, right? Start here, across the double bond, same side. So that kind of isomers are referred to as cis isomers. Is that clear? So cis means same. Now these days you hear this cis word a lot, no? Cis this, cis that, like so many cis. So we hear trans also a lot. In your generation, I don't think there was any other generation who has heard these two words than your generation. Anyone who is not doing science also now knows about these two. Back in the day, in my time when I was doing A-levels, only the chemistry students have ever heard of trans and cis, right? And now like even the art students, especially the art students know about cis trans a lot. So do you understand? Right, so at least remember the differences or similarities between the situations here, so that you can figure out what's trans and what's cis. Is that clear? So this is called trans, that is called cis. Take a new heading, geometrical isomerism. Oh, sorry, stereo isomerism.
So it's still cold for them.
Sorry?
It's still cold for them.
Yeah, I'm also a bit cold. We'll turn it off for a second. Right? I think that's also working. Huh?
Can't molecule rotate like this?
Yeah, you can rotate it like this. For example, imagine now I rotate this whole thing this way. Is it different? Like you are saying the back side of it, but it doesn't mean the arrangement. Like imagine this corner didn't come to, like, this corner. Do you understand? Now you are asking me, can't it rotate like this? Yes, it can rotate. Basically, it's not rotation. We say it's flipping. It can flip, right? But even if I take this molecule and flip it, still the chlorine groups are on two opposite sides. No? The entire molecule as a whole gets flipped, right? You turn it upside down. Still the chlorine groups will be opposite to one another. Here also the same. Chlorine groups are on the same side. If I flip it, they will be on top. But on the same side. Yeah. Good question. Right. So take down stereoisomerism. First of all, stereoisomerism. You can write in stereoisomers, connectivity between atoms are exactly the same. Connectivity is the same. However, due to different spatial arrangement of atoms, they give rise to different isomers. Then take a new heading, geometrical isomers. Under that, write down geometrical isomerism is present in molecules that has carbon-carbon double bonds along with carbon-carbon double bonds along with carbon atoms forming the double bond connected to two non-identical groups. Now let me explain that last sentence. I said geometrical isomerism is seen in molecules that have carbon-carbon double bonds, and carbons that are forming the double bonds should be connected to two non-identical groups. What does that mean? These carbons should be connected to two groups that are not the same. Why is that? Because imagine if they were connected to the same group on one side at least, if they were connected to the same group, like Tisar said, we can take this and just flip it. We get that. You understand? This, whenever you have the same identical group connected to one carbon with a double bond, you can't have cis trans. Is that clear? Because these two are the same. If you take this same molecule, now imagine this is in this format, I take it and let's say I flip it, then I get this. Do you see it? Right? So basically they are the same. Just because I flip something, that doesn't change anything. So if you have two identical groups connected to the carbon with the double bond, nothing. You don't get cis trans. Okay? Right. Take this diagram down. Take this diagram down, please. Instead of saying fixed arrangement of atoms, I'm sorry students, I just wanted to use a less advanced word here. Fixed conformation is better because atoms arrangement do not change in stereoisomerism. Conformation means this particular, directional arrangement is fixed. Connectivity is the same, like this way is fixed, right? You can't have atoms changing position through a rotation. That's what conformation is fixed means. Do you think you can stay till 7:15? Sorry, I need to at least give you the introduction of enantiomers so that we are done and we can actually look into questions. Next week is when? Next week is 23rd. I'm not sure whether they are open on 23rd that week. Maybe we can meet once before Christmas. Not Christmas, before New Year's. They close for a week or so. I'm not sure though. Let me double check. No, here we don't have a double bond. A single bond. My goodness, if you go home and see this, you'll be in trouble after that. There should be hydrogen on?
The other side. Not the. Cis isomer.
Yes. Yeah, earlier I just erased it, no? I forgot to rewrite it. Thank you. Are we done with this? Okay. So now, students, it's just a matter of identifying what is a cis isomer, what is a trans isomer, and then even naming them. Naming them is not that difficult. You write the normal, usual name of the molecule. Now, for example, what is the name of this molecule? Because it's drawn differently, now your brains are not braining, no, like I've seen, it's not functioning, because you're not the only ones. When I did this in the previous classes also, I've noticed they couldn't name this one, like, you know, like it's a bit difficult. What is the name of this molecule? Sorry? Yeah, a dichloroethene one. So basically, if you're being specific, we can be, there's 1, 2 dichloroethene, right? So since this is a trans isomer, you write trans dash 1, 2 dash dichloroethene. That's it. This is cis dash 1, 2 dash dichloroethene. Is that clear? Right. So now write a question down. Draw the 2 geometrical isomers and name them. Draw the 2 geometrical isomers for the following structural formula. Draw the 2 geometrical isomers for the following structural formula. And name them. So basically these 2 carbons have a double bond between them. Okay. Draw the 2 structural formula and name them, please. So draw the 2 cis-trans isomers and name them, please, quickly. Elevation on class second, why another? And Macaulay another. Okay. Sorry students, I just realized when I wrote the formula I have added additional hydrogen here, right? Sorry students, so this is going to be CH3 Cl CH3. Right, shall we quickly name this and quickly move on to the next part. I need to give you one more question from this and see whether you can think about different types of isomers that can be formed for the same molecular formula. So this one is what, students? Is this a cis isomer or the trans isomer? First of all, tell me that quickly. What is it? This is cis. Trans would be? This is trans. So now cis one, if you name it, can someone tell me what kind of molecule is this? Like, is it a ethene, propene, or butene? What is it? What is this? Who wrote this as a dimethyl ethene? Anyone wrote it as dimethyl ethene? Some did, like in previous classes. I'm not sure whether you all did. So this is a butene, right? So we have two substituents here, cis 2,3 dichloro but 2-ene 2,3 dichloro but 2-ene. This is also the same. The name doesn't change. If you number it, you can say 1, 2, 3, 4. Sorry, 4 is not here. This is a substituent. This is a substituent. Again, we have trans 2,3 dichloro but 2-ene. Name is the same, only difference is cis and trans versions are there for the same name molecule. Molecular name is the same except for the cis part and the trans part that goes in front of the name. So therefore we can argue that the name is different to one another because this is one type of molecule, that's a different type of molecule. Their chemical properties and physical properties slightly vary, right? They are not the same. Okay? Right. Now write a question under this, write another question. Draw another set of geometrical isomers. Draw another set of geometrical isomers using the molecular formula of the above molecule. Using the molecular formula of the above molecule. Now this is where you have to think. I'm going to erase this. When you're done, tell me. If someone is confident that they have gotten to an answer, also you can tell me. Whose pen is this? No. I'm sorry, I think you're making a small mistake here. How can this be CH2? Each carbon should have 4 bonds, so this can't be. It has to be CH3, okay? So therefore, there has to be a double bond here. You can't avoid that. There has to be a double bond. And each terminal carbon anyway definitely have 3 hydrogens, if there is no other groups attached to it. Because guys, keep in mind when you're drawing structures, each carbon should have 4 bonds. It is a must. Each carbon should have 4 bonds. You can't avoid that. Now these are, I asked you for cis trans. No, geometrical isomerism means cis trans, right? So that means if you have the same identical group attached to the same carbon, it can't produce cis trans. Okay, and plus these two are the same. Imagine now this one is there. Imagine you rotate it this way, you get this. Now again the same story. Identical groups can't be connected to the same carbon. It will not produce cis trans. If you have identical groups connected to the same carbon, it can't produce cis trans, or it can't produce geometrical isomerism. What is this? It's a new type of group. See, guys, now I'm going to have to somehow find some sort of punishment because this is getting out of hand. You can't invent stuff. Carbon should have 4 bonds. If a carbon is having double bonds, still it has 4 bonds. 1, 2, 3, 4. Right? If you are getting confused with this, condensed formulas, then draw it without condensing it. Right? Draw it without condensing it, so that you know, okay, CH3 means this. This is CH3. Right? When we just write CH3 or when you write CH2, you need to understand why we do that. Okay? Did you get one? This one?
This how much is there?
So, yeah, so these two,
They're the same.
they're the same, no?
Same.
They're the same. No. Again, if you put it here, this carbon is missing hydrogens, and here the identical groups are connected to the same carbon. Can't be. See, now this is why we say, don't. Now, have you all gotten worried about your critical thinking skills ever? You have not thought about it in a while, right? Maybe start thinking about it in a while. It's now time. You all have to start thinking, students. How many of you think, in general, think about situations? Like imagine you are presented with a problem. Let's say it could be financial one, saving up for something that you like. The festive seasons are coming up, right? Or if you have a problem, how many of you actually think rather than go running to your parents and asking for it? Right? Do you think about anything? Right? How can I just maybe save up cash or maybe do something to get that? Except for cutting class and collecting that. That's not thinking, right? So none of you do, I think. Now forget about the financial aspect of things, and when it comes to physics questions, you have to think a lot. How many of you how often do you easily get to the answers? So now if you all are with your phones a lot, I would say your thinking would now be slightly reduced, right? Because why? Not only you, adults also, we in general, I don't take myself off of the equation when I talk about these things, because we as adults now, we are also getting used to this, what you all do, staying on the phone a bit. So it's bad. right? So you all are hindering your thinking. There's nothing much to think about here. What we do is, what we need is, you need to attach two different groups here, and the same different groups are present in the other carbon as well. Now, what do we have, students? Imagine we are now have utilized carbons. So basically I have a CH, one carbon, three hydrogens and a chlorine. These are the options I have. I need to rearrange them to get two different groups here. Am I correct? Can't I take this carbon, connect hydrogens and one Cl here and another hydrogen here? You have done it. Very good. Very good. So if you have done it, that means you have not been on the phone a lot, right? So that could mean that you were paying attention as well. So I'm just joking about the fact that you guys are not on the phone. I'm pretty sure all of you were on phones a lot, but still have gotten to the answers. Right? Very good. So these are the two other groups. Now, don't think because I told you this model, you can now do any question with the same model. Keep in mind, every question could be different. And now you know one trick. That is getting a hydrogen here and shifting the functional group to other group. That's one trick. But the same trick won't work all the time. Develop your thinking. Okay? Same trick won't work all the time. Develop your thinking to get two different, to get two answers easily, especially when it comes to chemistry and physics. I'm not very sure about biology. I also have no understanding of maths. Maths definitely will need critical thinking, I'm pretty sure. But when it comes to chemistry, physics, I through experience would know that you need this. Otherwise, you will not be able to get two answers easily. Now, can someone at least name this for me? Tell me the name of this compound. Forget about the cis trans for the time being. Tell me the name of this molecule. This one. Name. What is the name? No, yeah, it's cis trans. This one is cis. This is trans. Yes. I'm asking name of the molecule. Okay, we'll start with cis. Okay, and then 1,4 dichloro bute. After that, 2-ene. Yes. Or else we can write cis 1,4 dichloro 2-butene. 2 can be brought in front of bute. 2-butene. Okay. So this one is going to be trans 1,4 dichlorobute 2-ene. Write down small homework and leave some space for it. Draw all the geometrical isomers for the following molecular formula. And name it. C6H10Br2. Okay. Now students, I don't feel right to let you all go without teaching you. I will not give you a note. Note will follow later. But we have come all this way to go home without learning about enantiomers, because when you learn about enantiomers, the lesson is done, completed. I know I can't give you a note and then question you on that today itself, so we'll do that later. But at least I want to cover the theory parts and complete the lesson. right? So, but the note is incomplete and questions will be incomplete. We'll do those next week if we have classes. If not, we'll do maybe a small online session. I haven't decided on it yet. We'll see. So anyway, now when it comes to the next one, it is called, I'll take 10 minutes. It is called chirality, or we are talking about optical isomerism. Optical isomerism is there due to a molecule containing a carbon atom that is bonded to 4 different groups. That is bonded to 4 different groups. Right, so do you see here this carbon is bonded to 4 different groups here. 1, 2, 3. All the groups are unique. There are no 2 similar groups here. So this carbon is referred to as a chiral carbon. Chiral. Now chiral carbon, or the word chiral, comes from Greek terminology. Chiral stands for handedness. Handedness. I would show you my hands, but it's all dirty with this black ink, right? So why do we say handedness? Why do we say chiral? What is the reason of using the word that is used for hands here? If you take your hands, the 2 hands are they identical to you? When you see them, they look similar, right? But are they, I would ask you this way, are they superimposable? Can you superimpose the hands? Now don't superimpose them like that. That is not for superimposing. Superimposing means like, trying to overlap the 2 and getting the same type of or them overlapping perfectly. Do they perfectly superimpose? Now if you try to superimpose, maybe about 3 fingers will superimpose the like the other 2 fingers. 3 will superimpose, maybe the other 2 will not, right? Why? Because they are not identical. They are mirror images of one another. Is that clear? So that is why the word handedness is given here, because whenever a carbon has 4 different groups attached to it, it actually has 2 different forms, and one form is the mirror image of the other. The one form is going to be mirror image of the other. You know how to draw a mirror image, right? So don't get confused here. This is ethyl group, CH2CH3 group. I have abbreviated it to C2H5, right? I have made sure that I write carbon here just because I want to show the connectivity between carbons and carbons, right? So if you want, I don't want to change it any further. This is fine. You understood, right? So when it comes to this form of the molecule and this form of the molecule are mirror images of one another. And if you actually make a 3D model of them and then try to overlap those 2 together, they will not overlap perfectly. Only 2 bonds will overlap. Maybe this bond and this bond will overlap. The other 2 are not overlapping, right? They are not going to overlap. So always keep in mind, only the carbons that have 4 groups attached to them has this situation going on. And these are called optical isomers. Actually students, when it comes to optical isomers, we don't like to call them isomers. We use the word enantiomers. Instead of the word isomer, we call them enantiomer. E-N-A-T-I-O-M-E-R, right? So enantiomer. So these enantiomers, although they look the same, they have similar physical properties, but they have sometimes very different chemical properties. Very different chemical properties. One unfortunate scenario was in 1970s. I can't remember whether the year I was correct. 1970s, if I'm not mistaken. For 1970s, 17s or 70s, I'm not sure. So basically, what happened was there was a drug that was formed for pregnant mothers, right? For nausea, for morning sickness. And this drug was supposed to, help them with headaches during pregnancy. But what happened was, this drug had this type of carbon. This type of carbon means what? Carbon with 4 different groups attached to it. Now, when you have carbon with 4 different groups attached to it, they form enantiomers, 2 different types of molecules. And their chemical properties are different. Back in the day, they didn't know that. Right? So then what happened? And plus the worst scenario is, whenever you are trying to just casually make or produce this molecule, any molecule with chiral carbons, when you're just usually producing them through a general process without being very specific, what happens is these 2 gets produced in 1:1 ratio, 50-50. Is that clear? So any mixture will have equal amounts of this and equal amounts of this. Now in that medication, one enantiomer actually helps with the headache, the other enantiomer mutates the fetus. So there were so many stillbirths, there were so many miscarriages, many birth abnormalities caused due to this medication. Real situation, right? Real past history, right? So because of that, then they realized the issue is with this medication. Only the mothers who took the medication had the issue. Why? One helps the child, one helps the mother, other attacks the fetus. Is that clear? Their properties are different. That's why. Chemical properties are different. See? Spatial arrangement. Connectivity is absolutely the same. The way in which now, in this case, the fluorine is going behind. These are based on the way that we have drawn here. Basically, they are not superimposing with one another, right? Here, I can't just say the fluorine is going behind, this is coming forward. That's not the case. Actually, they are drawn in a way that appears that as if they are going behind, but this is to the left, that is to the right. When you are trying to superimpose, this section tries to superimpose with this, but they are not aligning well. You can't superimpose at all. So because of these things, they are not the same. So students, these are called optical isomers. And usually these enantiomers are named L enantiomer and D enantiomer. Why we call them L enantiomer and D enantiomer and further details will be given to you later. All that you need to know is, any substance that has a carbon with 4 different groups attached to it can produce optical isomerism. Is that clear? And the 2 isomers that are produced are mirror images of one another. So at the exam also, if they give you one to draw the other, you draw a mirror and draw the mirror image. We usually draw the mirror also, right? It's something we do. So do that and that'll be fine. Is that clear? Understood? Right, I'll stop here. I think families must be waiting for you all to come. Right, so is that clear now? Okay, go home and read up on it. Go home and read up on and maybe confirm me the year. I can't remember now. Confirm me the year about the whole medication that I mentioned earlier, right? All right, so that will be all for today, everyone. We are essentially done with topic 7. We have to do more questions and we have to gradually move towards topic 8. Okay, so if there's anything that you need to clarify, drop me a message on the group, so we'll then discuss it there. Okay. That'll be all for today. I'll see you all again, hopefully, I think after Christmas, right? After Christmas, so happy holidays, everyone. I'll see you all next week after next, right? See you all then.